Suppose the electric charge density rho E is equal to 0, and also the current density is equal to 0. In this case, if we write down Maxwell's equations, then we have divergence of B equal to 0, curl of E equal to minus del B over del T, and divergence of E is also 0 because charge density is 0, and curl of B, because we have 0 current density, so curl of B will be 1 by C square del E over del T. Now these equations have a symmetry which is called electric-magnetic duality. In these equations, if we replace B with E by C, and if we replace E with minus CB, then we again get Maxwell's equations. This is obvious for these equations, divergence of B and divergence of E. For example, if in this equation divergence of B equal to 0, we replace B with E by C, we get divergence of E equal to 0. And if in this equation divergence of E equal to 0, we replace E with minus CB, we get divergence of B equal to 0. So consider this third equation here, divergence of E equal to minus del B over del T. If in this equation we replace E with minus CB, we get minus C curl of B, and on the right hand side we replace B with E by C, we get 1 by C del E over del T, with a minus sign because we have minus del B over del T on the right hand side. So if we simplify this, we get curl of B equal to 1 by C square del E over del T, which is this equation here. So if in this third equation, if in this equation we replace E with minus CB and B with E by C, then we get this equation, curl of B equal to 1 by C square del E by del T. Conversely, if we start with this fourth equation, curl of B equal to 1 by C square del E over del T, and in this equation if we replace B with E by C and E with minus CB, we replace B with E by C, so we get 1 by C curl of E, and we replace E with minus CB, so we get minus C over C square del B by del T. So we get curl of E equal to this C when comes to right hand side cancels this one of the powers of this C here, so we get 1 minus 1 del B over del T. So we get this equation if we replace B with E by C and E with minus EB, we get this equation. So we have a duality here, and this is called electric magnetic duality. Now suppose we have sources present, the current density is not equal to 0, and also the charge density is also not equal to 0. In that case, if we introduce, if rho E is not equal to 0 and JE is not equal to 0, and we introduce magnetic charge and magnetic current density as well, and write down modified Maxwell's equations. So suppose rho E is not equal to 0 and JE is not equal to 0. So the Maxwell's equations involving rho E and JE are, in this case, divergence of E equals rho E by epsilon naught, and curl of B equals mu naught JE plus 1 by C square del E over del T. Now if we also introduce a non-zero magnetic charge density rho B and a non-zero magnetic current density JB, then the other two Maxwell's equations can be written as divergence of B, which is 0 if rho B is not equal to 0, but if rho B is not equal to 0, then this will be mu naught rho B. And the other Maxwell's equation will be curl of E equal to minus mu naught JB plus del B over del T. So again we have four Maxwell's equations. This one first, second, this third equation, and this is the fourth equation. And in these equations also we have electric magnetic duality, similar to the case when the sources were 0. In these equations, if we replace, as before, if we replace B with E by C, we replace E with minus C times B, and also we replace the magnetic charge density rho B and magnetic current density JB with C times rho E and C times JE, and we replace electric current density rho E and electric charge density rho E and electric current density JE with minus rho B over C and minus JB over C. Then again these four equations transform into each other. So under these replacements, if we take any of these four Maxwell's equation and carry out these replacements, we replace by with E by C, E with minus CB, rho B is replaced with C rho E, JB is replaced with CJE, rho E is replaced with minus rho B by C, and JE is replaced with minus JB by C. Then we again get back Maxwell's equation. For example, consider the first equation, and divergence of E equals rho E by epsilon naught. In this equation we replace E with minus CB, so we get minus C divergence of B. On the left hand side we get minus C divergence of B, and on the right hand side we replace rho E with minus rho B over C, so we get rho E is replaced with minus rho B over C. We get C, and epsilon naught is already there, C times epsilon naught. So we get divergence of B equals rho B C square epsilon naught, but C square is 1 by mu naught epsilon naught, so we get rho B by epsilon naught, which is mu naught rho B, and this is the third equation here. So carrying out the replacements in the first equation, we get the third equation. Similarly, if we carry out these transformation in the third equation, we get the first equation, and if we take the second equation, for example, if we take the second equation, which is second equation is curl of B equals mu naught JE plus 1 by C square del E over del T. On the left hand side, B is replaced with E by C. We get 1 over C curl of E. On the right hand side, JE is replaced with minus JB over C, so we get mu naught JB over C, and we have 1 by C square. E is replaced with minus CB, so we get minus C del B over del T. So this gives curl of E equals, C cancels, we get minus mu naught JB, and this C again cancels this C here, we get plus del B over del T. So this is the fourth equation. Similarly, if we replace E, carry out these replacements in the fourth equation, we get the second equation. So the electric magnetic duality is still present when the sources are present. Sources are non-zero, but provided we also introduce these fictitious magnetic sources, rho B and JB. Now these equations become more, this duality, electric magnetic duality, can be expressed in a more in a simpler form if we write down Maxwell's equations using differential forms. So in differential form notation, the Maxwell's equations are df equal to 0, and in terms of Hodge star, differential of Hodge star of f differential is mu naught Je, where Je is a one form. We have not defined what this Hodge star operator is, but for the sake of electric magnetic duality, we don't need to go into details of this operator. If we introduce a magnetic current one form, then this first equation, first of all, if Je is equal to 0, if the magnetic one form equal to 0, then these equations become df equal to 0 and d star f equal to 0. So it's easy to see that there's a symmetry here, and this symmetry is f. If we replace f with star f and we replace star f with f, then these equations transform into each other. So in this case, this electric magnetic duality is simply replacing f with its Hodge star. If we introduce a fictitious magnetic current one form Jb, then we can modify this first equation, and Maxwell's equation in this case become Hodge star of df equals mu naught Jb over c, and Hodge star of d Hodge star of f equals mu naught Je. Here Jb in terms of rho b and J vector b is c rho b dx0 plus jbi dxi, I summed from 1 to 3, and similarly Je is minus 0 e dx0 plus Je ith component dxi, where I is summed from 1 to 3. So in these two equations, in the presence of non-zero magnetic current and non-zero electric current and current density, this electric magnetic duality takes this form. F is replaced with its Hodge dual, and if in the second equation Hodge dual of F goes to its Hodge dual, because on two forms Hodge dual square is equal to minus 1. So Hodge dual of f goes to minus f, and Jb, if we replace Jb with c times Je, and if we replace Je with minus 1 over c Jb, then these equations transform into each other. For example, this first equation, if we replace f with Hodge star of f, becomes Hodge star of d Hodge star of f equals, and on the right hand side Jb is replaced with cje, So we get mu naught Je, which is this second equation. And if in the second equation we replace Hodge star of f, means we are replacing actually f with Hodge star of f, and since Hodge star square is -1 on two forms, we get minus df, and on the right hand side we are replacing Je with -1 by cjb, -1 by c mu naught jb. This minus cancels with this minus, we get the first equation, Hodge star of df is equal to mu naught over c jb. So this is in this form of Maxwell's equations, this electric magnetic duality is related to the Hodge duality of differential forms.